17.70 ethylamine has a strong pungent odor similar to that of ammonia. Like ammonia, it is a Bronsted base. A 0.10 molar solution has a pH of 11.87. Calculate the Kb and the pKb for ethylamine. What is the percentage ionization of ethylamine in this solution? 3.2. All right. So to start off, what we're going to want to do is we're going to want to set up this equation right here. This kind of lays everything out for us. So, anyways, and we want to find the Kb, and of course, Kb is products over, no, not products, but OH minus over times CH3, CH2, NH2 over CH3, CH2, NH. All right. And what we're going to do is we're going to use an ice table. So, laying this out, water is liquid, so, or is a pure element. So, anyways, so we've got 0.10 molar of ethylamine to begin with. We're going to lose X amount, which will give us 0.1 minus X. And then we're starting off with none of that, and we're going to gain plus X. So an equilibrium, those values will just be X. All right. So going back to our Kb equation over here, we do not know what X is. If we substitute this in, we don't know what X is. But they give us what the OH negative is, which is great because they also gave us the pH. So we can use that to find the pOH and then find what OH is. So to do that, we'll come over here. They tell us that our pH is 11.87. pOH is just 14 minus that, which is going to be 2.13. So anyways, we know also that OH negative is equal to 10 to the negative pOH, which is just 10. Plugging this in to the negative 2.13 equals 0.007413. And so that is our OH negative concentration. So that is equal to X. Awesome. So we'll be able to plug that in over here into our Kb equation, and we'll have 0.007413 squared, because that is the value of X, and we've got X times X all over 0.10. And we were able to just make this assumption that X is going to be won't affect the value. It's so small that it's not going to affect this value. So, so we'll just have 0.10 right there. So anyways, doing the math right there, we get 5.5 times 10 to the negative 4. And that is our Kb value, which is great. They also want us to find the pKb value, which would be pKb is just negative log of Kb. So when we plug this value in there, we get 3.23 for the pKb. So there we go. And they also want to know, the percent of ionization of ethylamine in this solution. So that's just going to be moles ionized per liter all over moles available per liter. All right. And what we had there was the ionized. What ionized was our X value, which was 0.7413 is the amount of moles ionized per liter. So that's just going to be 0.007413 all over moles available per liter, which is 0.10. So do that, you get a fraction, times it by 100, and you get 7.4% ionized. So that's that. You're on.
Okay, 17.72. What are the concentrations of all the solute species in 0.150 molar lactic acid? What is the pH of the solution? And this acid has a Ka of 1.4 times 10 to the negative 4. So for a problem like this, we're going to use ice table. Basically, I'm just going to use ice tables for everything in this chapter. So just get used to them. They gave us our concentrations to start off with, our initial concentration here. We're not going to worry about water because it's a pure substance and it's not going to be a factor. And then we initially have none of this. So it's going to be 0. The change is going to be, we're going to be losing concentration of this, and we're going to be gaining concentration of these two. And then, so then you just like bring them together. There you go. That for your equilibrium concentrations. So then they gave us our Ka, which is 1.4 times 10 to the negative 4, and we're going to set it up with our product of our reactants. We're not going to include water. So that's going to be H3O times concentration of that over concentration of our lactic acid. So then if we just plug in our values for equilibrium concentrations in here, we end up with x times x, so x squared. Over in this, we can assume that the change is going to be so small to this that our minus x, we can get rid of it and just use our initial concentration because it's not going to, that's why it's called a weak acid, because it doesn't dissociate very much. So then when we go ahead and use this and this, to solve for x, we end up with x equals 4.6 times 10 to the negative 3. And x was our equilibrium concentration for both of those. So that means that that's the concentration for our H3O plus, which can also just be written as H plus, which is essentially what it is, and also for our anion concentration. And then they also want to know the concentration for our lactic acid, which then you'd go ahead and plug in the X because they do want to know the exact. And it ends up roughly being, so you're going to just take and plug in here for X. And so your concentration for lactic acid ends up being 0.145 molar. So barely a change. And then they want also to know the pH. So you just, to get pH, you just take the negative log of the H concentration, the hydrogen ion. So the negative log of that number, which is going to be equal to 2.34. Not that.
Codeine, a cough suppressant extracted from crude opium, is a weak base with a pKb of 5.8. What will be the pH of 0.02 molar codeine? Use code as symbol for codeine. All right, excellent. So they gave us the pKb. And they told us that that was 5.8. And so from that, we're able to find out what Kb is, which is 1.58 times 10 to the negative 6. And just setting up our equation here, we got products over reactants. For the equation, just kind of outline of setting the stage here for this problem, really. And here's the equation. Of course, we're going to use an ice table. So let's get down to the ice table. Here we go. Fatal water is just kind of discount water there for that. In our ice table, we got 0.02. We're going to be losing concentration, so it'll be 0.02 minus x. We got nothing to begin with, so we're going to be gaining concentration for products, and we'll just be left with x right there. Excellent. All right. So let's see what we got here. They want to know what will be the pH of the solution of codeine. All right, so pH. So first of all, what we're going to want to do is we're going to want to solve for X. If we can solve for the equilibrium concentration of OH negative, then we'll be able to find the POH and get the pH out of that. So this is our goal, is to find what that X value stands for. So we're going to use the Kb equation over here, and we can just simplify this here. We've got OH negative, which is X, times H code plus, which is the X, so we're X squared over 0.02 minus X. All right, and we're just going to make an assumption that this X isn't going to change much. So we'll be fine. And then if we do that, we've got it equaling 1.58 times 10 to the negative 6. And therefore, we can conclude, doing a little algebra, that X is equal to 1.8 times 10 to the negative 4 molar, which is, again, our OH negative concentration, which is fabulous. So from that, we'll be able to find the POH. POH, remember, is negative log concentration of OH negative, which is just plugging this value right there. We'll get 3.74. And pH is just 14 minus that. So that's just going to be 10.26. And that is our answer, and that's how it's done.
All right, everyone. This is 17.76. It says that a solution of acetic acid has a pH of 2.54. And it wants to know what is the concentration of acetic acid in this solution. So it sounds like a small, easy little problem, but it really isn't, unfortunately. You know what? 0.54. Basically, that tells us our concentration of H ions, because we can take the pH, and if we just raise it, or 10 to the negative of the pH gives us our H concentration. So that's going to be 2.9 times 10 to the negative 3 molar, which is going to be the concentration of our H ions. Because the negative log of this is that, and so if you take 10 to the negative of that, you get that as algebra with logs. It's kind of confusing, but that's what it is. So the equation that we're looking at is acetic acid in water is dissociating into H ions and acetate ions. So they are asking for the final concentration of acetic acid. So we're going to use an ice table here, as usual. Now, this ice table is going to be a little bit different because we don't know this concentration. So I'm going to go ahead and just call this concentration question mark. You can just call it that. In brackets, you can call it A, you can call it Z, you can call it star, it doesn't matter, just mark that we don't know what it is. And then these are going to be 0, just like usual. And so we know that this is changing. We know that we still know it's getting smaller, so it's going to be minus x. So, and these are going to be getting bigger, so it's plus x. Down here we're going to have question mark minus x, and here we have x and x. So it's basically the same as the ice tables we usually do, but we just don't know what this is. What we can do is look up what the Ka is for acetic acid. It's in a table, I believe it's table 17.2 in the book. I can't think what page that's on right now, but the Ka tells us is 1.8 times 10 to the negative 5. And then we're going to set up our equilibrium thing here. So products over reactants. And so what we're going to do is plug these equilibrium concentrations into that, so that we end up with 1.8 times 10 to the negative 5 equals, these are both x's, so it's going to be x squared. And this we're going to assume, since acetic acid is a weak acid and it doesn't dissociate that much, we're going to assume that it doesn't change enough to really make a difference. And so that's just going to be question mark instead of question mark minus x. Now what we do know, because of what they gave us, here is the concentration of H+, which is x. So since we know x, we can plug x in here. So that was 2.9 times 10 to the negative 3. That's going to be squared over question mark equals our Ka that we got at the table. Sorry, that's a horrible 8. And then we solve for the question mark, which is actually just concentration of HC of acetic acid. Which I guess if I was being really thorough, I would have just written that in all the places of all the question marks, but for the sake of just for the sake of time. I mean, just for as a first one. Anyways, so when we solve for that, we end up with 0.47. And that's the answer. Hey, Michaela.
Yeah?
Why do all the chemistry teachers teach about ammonia?
I don't know.
Because it's basic material.
So true. So true. All right. Today, this evening, or whatever time it may be that you're viewing this, we're working on 17.78. This is a great question. Let me read it to you. What is the pH of a 0.005 molar solution of sodium cyanide? All right, that's a good question then. Well, I don't know. So let's work this out, shall we? Got our equation right here. Kind of lays everything out for us. And from that, we're going to get our Kb equation, so the reactants, same thing. And what we want to do is we want to find what the Kb value is. So what we're going to do is we know that Kb is equal to Kw over Ka. And we're going to use the table in the book to find out what the Ka value is. So we know that Kw is 1 times 10 to the negative 14. And looking at the Ka value there, we get 6.2 times 10 to the negative 10. Simple math gives us the Kb, which is 1.6 times 10 to the negative 5. So that's what we get for our Kb value. So we're going to set this up where we have, I should have done my statement here. So we started off with let's see here, 0.005 molar negative x, 0.005 minus x plus x. Just setting up our ice table here, given the information that they provided. So anyways, now we're just going to substitute these values in right here for our Kb. So we're going to end up with x squared over 0.005 minus x. All right, and then you know that, as we found earlier, it was 1.6 times 10 to the negative 5. Little math tells us that maybe we'll calculate that we can simplify. We're going to make it a simplification right now, but we'll later find out that we won't be able to do that. So anyways, when we do this math, we find that x is equal to 2.8 times 10 to the negative 4, which is equal to the OH negative concentration. But this is not significantly smaller than our initial concentration for cyanide. So we're going to do what they call successive approximation. So we're actually going to plug this in for the x value. So we're going to end up going x squared over 0.005 minus 2.8 times 10 to the negative 4. And from that, we're going to find out that our x is, we'll set this up, this is equal to 1.6 negative 5, and then we find out that x is equal to 2.7 times 10 to the negative 4. Again, we're going to plug this x value in as the x, so we're going to get x squared over 0.005 minus 2.7 times 10 to the negative 4, and we're going to get 6, so that equal to 1.6 times 10 to the negative 5. And for our x value, again, we're going to find 2.7 times 10 to the negative 4. So that is our x value. And again, we did this successive approximation because our X value was not significantly smaller than the initial concentration, so we couldn't, this initial simplification is not, can't use that. So we're going to go through, plug X in for the actual values that we find. So find out that X is equal to 2.7 times 10 to the negative fourth, and from that, we'll be able to find out what the POH is. Again, POH is just the negative log of the OH negative, which is 2.7 equals 3.56. From that, we can find the pH. 14 minus 3.56 is equal to 10.44. There's our pH. There we go. Hey, Jacqueline, how many moles are there in guacamole?
I don't know, how many?
I don't know, just avocado's number.
That's a good one. Alright, we're gonna do 17.80 now. And it's a really long question, but to show you how as hard as it looks. It says the compound para-aminobenzoic acid, or PAPA, is a powerful sunscreening agent, and salts were once used widely in suntan and screening lotions. The parent acid, which we may symbolize as H-PABA, is a weak acid with a pKa of 4.92. What are the concentration of hydrogen and pH of a 0.03 molar solution of this acid? So first off, they give us the pKa, which is 4.92, and we are gonna need the Ka in order to answer the question. So what you do to get, anytime there's a P, it just means that they took the negative log of the original thing. So if you have pH, POH, pKa, pKb, whatever, all that means is they took the negative log of the original, like Ka, Kb, or whatever concentration. So what you do to get back to the original is you just raise it. So the Ka is going to be 10 to the negative pKa. So in this case, the Ka is 10 to the negative 4.92, which gives us 1.2 times 10 to the negative 5. So now that we know our Ka, we're going to use an ice table. Here's our equation. When we put our acid in water, we get hydrogen ions and PABA. So I don't really know if that's how you say that, but I'm going to say it like that. So our original concentration for H-PABA is 0.03. We have none of this and none of this. We're not going to count water as usual. So our change is going to be X's. So we're going to end up with 0.03 minus X and then X and X. So then here's our equilibrium law for the acid. Ka is products over reactants and equals to our Ka that we solved over there from the pKa. We're just going to plug these things in. It's going to be X times X, which is X squared. And then we're going to just assume that this is so small that that's not going to matter. Anyways, so we're just going to use our 0.03 here. And then that's so we're going to solve for X. We get 6 times 10 to the negative 4 molar, which ends up being our concentration of hydrogen ions, which I'm just going to write H+. So once we know our concentration of hydrogen ion, which is one of the things they ask for, they also want the pH, so it's just taking the negative log. When you do that, you get pH is 3.22. That's that. Hey, Michaela, you want to hear a joke?
Yes.
All right, so a neutron walks into a restaurant and orders, and then when she's done, she asks the waiter how much she owes him, and he says, "For you, no charge."
Oh, so love it. So great. It's so distracting. I don't know if I'll be able to focus on this next problem. But we'll give it a try. We'll go for it. We're working on 17.82. And the question is, calculate the pH of 0.2 molar NaCN. What is the concentration of HCN in the solution? Well, that's a good question. But we can do it using this blessed ice table that we have here. Oh, so great. All right, let's just plug in some numbers that we know. Initial concentration of CN is going to be 0.2. We got negative X, we're losing concentration, given. And then it's just going to be 0.20 minus X. Over here on the product side, well, zip, and we're getting concentration, plus X, X, and X. So this is great. So first thing that we're going to do is we're going to look up the Ka value in the table in the book. And we find out that the Ka value for this is 6.2 times 10 to the negative 2, which is great because we're going to be able to use that to find the Kb value. Let's remember that the Kb value is equal to Kw divided by Ka, which is 1.0 times 10 to the negative 14 all over 6.2 times 10 to the negative 10 equals 1.6 times 10 to the negative 5. I'll be right back with you in just a second. And what we're going to do with that is we find the Kb value, right? Yes. This is what we just did. Yes. So we're able to plug this number in to over here. So we've got Kb is equal to this equation. And we're going to use that to plug in our equilibrium value. So we got x squared all over 0.20 minus x equals 1.6 times 10 to the negative 5. A little algebra there. And we're going to find out that the x is equal to 1.8 times 10 to the negative 3 molar. And that is our OH value. And from that, we're going to be able to find the POH given, which is the POH, remember, is just the negative log of this. So that equals 2.74. And from that, pH is again 11.26. 14 minus 7. There we go. That's how it's done.
Alrighty.
Hey Jacqueline, what do dipoles say in passing?
I don't know. What do they say?
Have you got a moment? Ba-ding, ching!
Oh, that was great. Alright. Let's get on to the problem here, Michaela.
We're getting carried away. Oh, good times here. Loving it. All right.
Some people come in to see us. That was sarcastic. Alright. We're doing 17.84 now, and it says calculate the pH of 0.15 molar CH3NH3Cl for methylamine, which is CH3NH2, and it gives us the Kp. So this looks kind of confusing at first, but it's really just exactly the same thing we've been doing. Basically, this is a salt when it is in water. So basically it'll just dissociate, and then this here is actually an acid. You can tell that it's an acid because it has NH3, and those are usually acids because they'll give up an H to become an NH2 compound. So that's kind of like your clue. So basically you have to assume that those dissociate into chlorine ions and this. And the chlorine ions aren't really going to do much in the solution, so we're not going to really show that. But then this goes on to dissociate again, and it acts as the acid. It gives up the proton. So we're going to use an ice table as usual. It says that we start off with 0.15 molar. And then this is going to be 0 for initially. We're going to change like this. You guys should be pro with this by now because this is what all the problems have been, basically. They give us the Kb. We want the Ka because this is, we're talking about an acid reaction right now here. So Ka is equal to Kw over Kb. Kw is something that you should have memorized pretty much. It's just 1 times 10 to the negative 14. And then the Kb they give us. So when we divide that, we end up with 2.3 times 10 to the negative 11 for our Ka. So I'm going to forego writing the whole equilibrium law. You guys should know what that is by now. I'm just going to use the equilibrium values here. And so it's going to be x times x on the top, which is just going to be x squared. And then this is super small, so we're not going to bother with the change down there. And we're just going to write 0.15. Make it equal to the Ka. And then we're going to solve for x. Our x is 1.86 times 10 to the negative 6. And x is equal to our concentration of hydrogen ions, which then if we take the negative log of that, we can get our pH, which is 5.73. Hey Michaela, you want to hear another joke?
Absolutely.
All right, so two atoms are walking down the street, and one atom says to the other, I think I lost an electron. And the other one's like, are you sure? And he's like, yeah, I'm positive.
Love these. Oh, these are just great. Add a little spice to my life. All right, here we go. 17.86. A 1.8 molar solution of sodium salt of nicotinic acid, also known pharmaceutically as niacin, has a pH of 0.905. What is the Ka value of nicotinic acid? All right, they give us the pH at 9.05. From that, we find the pOH, and from there, we're going to transition over to a nice table. Surprising? I don't think so. All right, 1.8 is they give us for the initial solution there, and that's going to lose concentration. So we're going to have 1.8 minus x. Over here, nada for the products, but we're gaining concentration. And then, yes, x and x. Excellent. So we're going to do, we got our Kb solution, our equation here. Let's plug in some values, shall we? X squared, all over 0.18, because we assume x is not going to play a significant factor here. And from that, we're gonna have to solve some things. Okay, so x. We don't know what x is, but we can find x because that is the OH negative concentration, and we know the pOH. So let's do that, shall we? So we know that pOH is also equal to, well, let me rephrase that. OH concentration, negative, is going to equal to 10 times 10 to the negative pOH. So plug and chug, and we've got, plug that value in right there, and we will have 1.1 times 10 to the negative 5. And that is our OH negative, which is also equal to x. So we're going to plug x in here. So we've got 1.1 times 10 to the negative 5 squared all over 1.8. And that equals 7 times 10 to the negative 10. Fabulous. But they want to know what the Ka value, or yes, what the Ka value is. So remember, Ka is equal to Kw divided by Kb. So we know what Kw is, 1 times 10 to the negative 14. That's negative 14, that's a given. Kb divided by Kv, well, that's what we just found. We just found the Kv. Let's plug that thing in. So we're going to plug that in. And we're going to find out that it is equal to 1.4 times 10 to the negative 5. All right. So there you have it. Find the Kb using the pOH, and then Kw divided by Kb. Hey, Jacqueline, want to hear another chemistry joke?
Yes?
What do you do with a dead chemist?
I don't know, what do you do?
You bury him. Bury him. Let's see if we can find it on there. Oh, you know.
Over there, 56.
Oh, 56, of course, our favorite.
Oh, man.
You bury him. You hear that, Dr. Scott? Oh, so funny. Anyways, all right, we're getting, once again, too carried away.
88. Oh, it's a really long problem on paper, but I think we'll get done with it quickly. All right, this is what it says. Liquid chlorine bleach is really nothing more than a solution of sodium hypochlorite, which is NaOCl in water. Usually, the concentration is approximately 5.1% sodium hypochlorite by weight. Use this information to calculate the approximate pH of a bleach solution, assuming no other solutes are in the solution except sodium hypochlorite. And we're also going to assume that the bleach has a density of 1 gram per milliliter. So basically, we're going to do exactly what we've been doing, but they don't give us a concentration in, they don't give us a molar concentration, they give us a percentage by weight. So we're going to go back to the beginning of our time in chemistry and do some dimensional analysis. So they told us that it's 5.1% by weight, so that's 5.1 grams per 100 grams of solution. Then we're going to go ahead and say that that's 1 mole. And using the periodic table up there, we find the molar mass, which is 74.5 grams. Sodium hypochlorite. We're assuming the density is 1 gram per milliliter, and then there's, of course, 1,000 milliliters per liter. So then our grams are going to cancel out, and we're going to end up with moles per liter, and this gram cancels that gram, and milliliters and milliliters cancel, so we end up with moles per liter, and we end up with 0.68 molarity of NaOCl. And since this breaks up into Na plus and OCl minus, you can see that if there's 0.68 moles of that, then there will also be 0.6 moles of that because it's all 1:1 ratio. So that's where we're going to plug that into our equation over here, because we're talking about a salt here. So this dissociates, as I just showed, and then this goes on to pull a hydrogen off of water, and that's why it's a base. So that's what happens when it's a salt. You just have to see that the Na is going to do nothing in the water, the sodium ion, but that the other part is going to grab an H and be basic. So we got our original concentration, which is 0.68 molar. These have no initial concentrations. There's our change. This is all basically exactly what we've been doing. They gave us the Kb, we need the Ka, so that's Kw over Ka. Or actually, sorry, they didn't give us anything for K. We got the Ka out of table 17.2. We put it right here so that we can get the Kb, because Kb is Kw over Ka. So what we end up with is 3.3 times 10 to the negative 7 for our Kb value. Then if we plug that and we plug these into our equilibrium law, I'm not going to write it all out. It's going to be products over reactants, so it's going to be x squared times, and then we're going to assume that since this is so small, change is negligent. It's going to be over just the initial concentration, and it's going to be equal to that. So we're going to solve for x. X is going to be 4.7 times 10 to the negative 4. X is our OH concentration. So we can get pOH if we take the negative log of that number. So our pOH is going to be 3.32. And then since we know that pOH plus pH is 14, if we just take 14 and subtract, you get pH equal to 10.68.
What is the pH of a solution that contains 0.15 molar of this substance and 0.25 molar of that substance? Use Ka is equal to 1.8 times 10 to the negative fifth for that. All right. That's kind of vague, but those are long compounds. Can't name them all.
That's acetic acid.
Oh, duh. Okay. That was the joke for today. That was the joke for this one. Acetic acid. That's it. All right. Here we go. Well, they tell us straight up we're going to use the ice table. They don't tell us we're going to use one, but we know we're going to use one. So 0.15 negative x, 0.15 minus x, 0, 0, plus x plus x. All right, awesome. So we're going to use these equilibrium concentrations, plug them in for our Ka equation. And they told us what the Ka value was, so there we go. Just plugging those values in, we get x times 0.25 plus x. Wait a second. 0.25, sorry guys, my bad. I get in the habit. Plus x. Okay, there we go. So, yes, products over reactants. 0.25 plus x all over 1.5 minus x. All right, fabulous. So this is what we're going to do for this one right here. We're going to assume that these x's aren't going to affect anything because, you know, it's just a rule. Because K is so small that x value won't affect us. So we're good. So from that, 1.8 times 5 is what that's equal to. And so from this right here, we're just going to solve for x and do a little algebra. We know that x is going to be 1.1 times 10 to the negative 5 molar. And that's going to equal the H plus concentration. From the H plus concentration, we know that pH is equal to the negative log H plus, which is equal to 4.97, and that is the answer. Simple enough.
Awesome. Should we send them away with a motivational chemistry thought?
I think so. Jacqueline, would you enlighten us, please?
All right. If you're not part of the solution, you're part of the precipitate.
Ouch. I hope none of you out there are precipitates.